Hello and welcome everyone to today's episode. Today we are going to be covering the following topics. All the timestamps are in the description below. And I hope you enjoy today's episode. So let's get started on these topics. Let's try and understand the most simplistic machine learning algorithm, which is the linear regression algorithm. Now, you don't need much mathematics or computer programming to know or understand this machine learning model. And this is your beginner step to start machine learning. So let's say you're trying to predict house prices based on the size of the house. The house size is based on square feet. That's just a measurement and you don't really need to worry about that. It could be on any measurement that you want. But let's say we base it on square foot of the house. And the price over here, we are keying it in thousands. So this is 200,000, this is 250,000, this is 300,000. So we just put this in a data frame. And what the data frame does is it converts this into columns. So if we were to run this, over here, you can see the output that we get is in a column format. Then we are going to put them in these two variables. These are just standard computer variables in Python. And then we are going to run this function over here, linear regression. We didn't write this function. This has been written by data scientists who know how linear regression works. We just pass it to parameters x, which is basically the size of our house, and y, which is the price. Now this data we have, this is the past house prices sold, for example, on our street. So this is the past data. When you run this, what will happen is it will calculate that, and you can see it pretty fast because we have a small data set over here. Now what we can do is we can use that to predict our house price. So if we have a house with a zero size, then you'll get an output like this, which is says $58,000. Now the reason it does this is because you have an intercept value of 58. Basically that's your base price. So that's like, the minimum price for anything. What you might say is a starter price. But every time the house size increases, it will go up by 0.34. So if we change this to a 1, for example, here, you can see it's gone up slightly to 58.83 from 58.59. And if we increase that to 2, you can see that it keeps going up. So let's now try and do a house price for 1,000 and 1,000 square feet. So if we do that, then the house is worth 292,000, which is pretty close. So 1,292, yeah, that's pretty close. 300,000 pounds what it was sold for. So that's close enough. And finally, we can see like our score for the accuracy of the model. It's 0.98. So that means it's pretty accurate based on the data we had originally supplied to it and the predicted prices. So although, for example, here it's off by, 8,000 pounds, $8,000, that doesn't really matter because we know it's not 100% accurate. So that's what machine learning is. The question I often get asked about machine learning is accuracy. So this is a very simple linear regression machine learning model that we try to build. So here we just have the size of the house and we have the price. So a house, for example, that is 1,000 square feet is worth 300,000 in whatever currency that you want to use. But in this instance, let's use dollars, or if you prefer pounds, so 300,000 pounds. So here a question becomes is when you then build the model. So building a model is very simple for linear regression. You just apply the size and the price, so x variable and y, and then let the system basically execute this command and then run this command. It will build the model based on the data we supplied. So our data set is quite small. So as you can see here, we just have about 5 rows starting at 0. And if you then try and predict a house which has a size of 1,000, and in our data point, you can see a house that is actually 1,000 is worth 300,000. So that's the price of the house if it's that size. So when we then use our model to predict that same size and we say give it the price, it comes back with 292, not the 300,000 that exists within the data. And you might go, well, that's pretty bad because that's 7,000, difference between the actual value and versus what we got. And it's $7,000 or pounds is a lot of money. So when you look at the accuracy of this model, it goes that it's 0.98. So this is the model accuracy, and you can get this from over here, the score over here. So when it's getting accuracy of 0.98, so remember, anything closer to 1 is perfect prediction. Anything that is closer to 0 is no better than guessing or finger in the air job. So remember, we are not trying to get to 100% accuracy with machine learning. What we're trying to do is, rather than make finger in the air guess or estimate, we are actually using some logic behind this. So we are actually doing line of best fit, and based on that, we are trying to predict a house price. So although 7,000 pounds or $7,000 may seem quite a lot of difference between, the price, actual price, price and versus what the algorithm is predicting, that's actually pretty good because it's better than finger in the air job. So somebody's, you might ask somebody, my house is 1,000 square feet. What do you think it's worth? Well, they might say, you know what, I'm going to just make up a figure. So rather than making up a figure, why don't we just use the existing data that we have and based on that predict what the price could be? So this is better than guessing, I suppose. And that's the important thing that you need to be aware of. In my previous video, somebody asked me to explain what this model accuracy actually means. So what this model accuracy actually means is, for example, if I scroll up here, you can see that these are the actual house prices based on the size of the house. So if you look at this one, a house that is 1,000 square feet, its price is actually 300,000. So this is the actual past data. But when we create this model giving linear regression over here, and we make this line kind of fit the points based on the size of the house and try and predict the price, what the model does is, model is never 100% accurate. So if we look at this, we got an accuracy of 0.98. This is because if you have a look at this, the value actual 300,000, actually the model predicts it to be 292. So you know that it's not 100% accurate. So this figure here, what do they actually mean? All it means is there's some maths behind this, which you can see here. Now, this is the manual way of doing it. So this is how you calculate the R2 calculation manually. And I basically use this sklearn metric library over here and R2 score to do the same thing. And it came back with the same result. But you can do it manually using these formulas over here. In simpler terms, all it is based on the past prices and based on the predicted prices, what it's doing is dividing one by the other and saying, okay, if I were to not use any model and just take the average house price, then is that better way of doing it versus what the model is predicting? Because the model, remember, is a straight line. They will try and fit all the points on a line. And that's why when you divide one by the other, you get this accuracy here. And remember, the accuracy is if it's close to 1, that is perfect prediction. If it's closer to 0, then it's no better than guessing. So that's the formula. If somebody asked how do they actually work, this is how it works. And I'll explain it a bit more around this calculation so you can actually understand how the R squared metric actually works. And that's basically the accuracy of the model. This is how you would calculate it manually versus using the sklearn metrics library. So remember, you can always do things manually if you wanted to. These libraries are purely there to help you go faster, so you don't have to remember all this maths that happens here. So in short, remember, it's just trying to work out based on an average guess, based on the actual data versus the predicted data, which one gives the more accurate result. So if you were to just take an average of these prices versus actually average of these prices, which one is better? Let's have a look at this R2 calculation in more details. So we can see this is the accuracy of the model, but how does it work? So this model we have here is based on house prices. So based on the size of the house, we work out the price. So this is the actual data. And the model is a linear regression model, which is basically predicting the house prices based on the past data. So it's saying the model accuracy is 0.98. So the calculation for this is there are shorthand ways of doing it using this library in Python. But if you wanted to do it manually, this is how you do it. But the individual steps are broken down even further. So for example, so these are your actual house prices. And what you do is you guess the average. So this is you take the numbers, you divide them by 5 because there is 5 of them. And this is the output that you get over here. Then see how far you are from the real number if you always guess the average. So this is the average. So you can see here that this figure over here is now what we're doing is we're taking that house price, individual house price. So in this case, 200 here, minus 300, which is the average guess. So this is the average price. And then you get this difference. And you get these differences for all of them. And then what you do is you total up the differences. So that's now over here. And then what you do is use your model to predict the sale for each day. So now this is the predicted figures. So back in our code where we predict the house prices, and these are our predictions over here. So what you get is 207 a year, for example. So these are our predicted values. So what you do is with the predicted values, you then work out the same thing, which is how far are you all based on the predicted value. So remember here, we worked out based on the average, but now we are working out for each of the actual house price over here. So these are the actual prices. And then we are minusing based on the predicted ones over here using the model. So you minus that and you get the differences over here. Now notice here we are squaring the differences. So to make them a bit more prominent. So basically penalizing the mistakes, and then you basically total them up. And once you've totaled them up, what you do is you divide this total of the differences between the actual house price versus the predicted, and you sum that up over here, and then you divide that by your average guess, and that gives you a score of 0.98. So why do we divide by this number over here is your question. This is what you might say is your average guess. So based on if you were to randomly guess the prices versus using the model, then what we're saying is this model is very good at predicting the house prices. It is 98% better than your average guess. So rather than just asking your friend to guess the house price, the model that we have built using linear regression is 98% accurate, or 98% versus the average user's guess. So if a user were to guess it, then we predict that based on that, we are likely to be 98% better than the guess. So that's why 394 divided by this gives you 0.98. And remember, we're doing 1 minus here. So this is a very small percentage. So you take 1 minus this number over here, which gives you 0.98. So again, let's continue our discussion on this model accuracy failure R2 value, which a lot of people in linear regression and machine learning get confused about. So 0.98 accuracy, what does it actually mean? So when we work out and when we look at this calculation, it may go over our head and we go, what in the world is going on? So let's break it down. This is all for calculation, and see my previous video when I go through it in detail. But when we work out this accuracy and we get this figure 0.98, 0.98 accuracy, what do they actually mean? And this is the important thing to understand. If you were to ask a friend, so let's say these are the actual house prices. So these are the house prices, and you divide them by 5 because there are 5 prices. Then this is what somebody looking at a street, they go, well, actually the houses in the street are worth 300,000. Then based on that, the user comes up with an average. But what you have is you have the actual prices, because this is the past data. Remember, you build your machine learning models on the past data. Nothing comes out of thin air. It has to be based on something. So it's based on the past data. And then you say, well, based on the data, then the difference between the actual price of 200 versus what an average user may guess is this much. And you might go, well, that's 100. So the difference is 100, but you square it. Why do you square this? This is to enable your error to become more prominent. So it's like making this mistake at school. If you make an error and you want the student to really realize that they've done this wrong, then you want to penalize them. So rather than taking 5 points of them, you take twice. So you take 10 points of them, or you take 100 points of them. It's up to you what you decide on the penalizer. But a standard has become is you square it. This is just something mathematicians have come up with. You could cube it and so on, but standard has been to square it. That's what we'll go with. That's what have been agreed in the wider community. So when you square this, then basically all these errors, so the error here, the difference between the 100 gets multiplied to, squared to this number, and you add these up, and this is your average error. And you do the same thing with your model. So with your model, it predicts the prices, and you go, oh, actually the difference here is 7, but since you square the number, it becomes 49. And then you do the same thing for each actual house price. So here, 200, 250. Remember, our actual prices were here. So you keep doing that, and then you get the same total. So when you look at this error versus this error, 25,000 versus 394, which one is better? You can immediately tell from the numbers that 394 is lower. So that means there are less errors in predicting versus the errors based on a complete guess. And what do we mean by, well, it's not a complete guess. It's based on the average. So this is the easiest way somebody could guess something. If you take the prices and then you divide them by the total number, that is the average. Yeah. So by taking the average, that's best guess. Just imagine your friend throwing a plane, and whose plane goes the furthest. So you go, oh, actually, this time you've done 5 meters, this time you've done 10 meters. So I'm going to say on average, you've done, 6 meters and so on. But that's how averages work. And that's what your best guess is. And then the model guess is actually better. So it goes actually, 394 versus 25,000. And then once you take a percentage, you divide one by the other, you get a tiny 394 at a percentage of this one is very low percentage. And then you just minus it from 1, which gives you 98% accuracy. So what we're saying is based on this 394, this is a very low number. So it's only, a fraction of the original 25,000, which is a very low error rate. Then you could turn that around and say, well, 1 minus, so basically 1 minus that tiny number that we get as a result of this, I mean, this is 98% accurate. And that's what we mean by model accuracy in machine learning linear regression model. So when looking at the R2 measure over here, you can see that the calculation for this, when done manually, works out as per my previous explanation. So what you're doing is basically taking the actual values, and then the model predicts, and then you compare the actual versus the predicted, but you also do it on what if it was a pure guess. So based on the average guess, that is the average average price of a house, how does that compare against the model prediction? So what we end up with is a situation like this, where you have the model is predicting an error rate of 394 divided by the 25,000 here. So this 25,000 is based on average guesses total error. So you can see the ratio is pretty small, but you need to understand these numbers over here, 394 and 25,000. These numbers themselves aren't the average dollar error. So these are not dollar amounts. They are used to calculate the R2 figure over here, which tells you how good your model is compared to guessing the average. So this is guessing the average, and this is based on the model. So when you take that ratio, that's what gives you this figure over here. So these are not dollar amounts. So you can't say the prediction error of the model is always, for example, if it estimates that house price is 300,000, you can't say it's off by $394,000, for example, because that's not what this actually means. So 394 over here is the total squared error for your model's prediction, because remember, over here, what you're doing is you're squaring the numbers. So this is the guessing squaring. So here, when we get to this 25,000 figure, what essentially is happening is you say, okay, the actual value is 200, and this is the guess value. Get the difference of 100, and then you square it. So you can't treat it as dollar value. And same with the model prediction. So if the actual value is 200 and the model predicts 207, so that's 7 multiplied squared. That's 7 squared, which gives you 49. So these are not dollar amounts. So it's important to understand this when using linear regression. So you can see all these, what you do is use basically, so this is the error rate, and the reason we square them is to make the error appear larger. So it has a larger effect on it, just as you do with the guess one. You do the same with the model prediction, and what you end up with is you sum the total amounts up. So 49 over here plus 64 plus 49, and then you end up with this figure over here. And so this, in essence, what the R2 is, it tells you how good your model is compared to guessing the average. So that's why we do this R2 calculation over here. So just make sure you don't understand it as dollar amounts. It's just a ratio. So don't treat it as dollar amounts, please. And the R2 figure itself, the closer it is to 1, the more accurate your model is. The closer it is to 0. So this one is pretty close to 1, because when you round this up, as you know, this would be 1.0. So the closer it is to 1, the better it is. So one of the things we talked about previously is this R2 calculation and how this ratio over here is derived. But notice here what we're doing is we are simply getting the actual price here, which is 200, and based on the average house price, and then what we do is we square the number, and it gives you the square of that number over here. But these are this error rate of 25,000. So what we're saying here is if the average house price, yes, is 300 by user. So let's say, the street, and on that street, the following are the actual house prices. What you do is you divide by, to get the average, you divide by the total number of houses, and you get a price of 300. If you ask somebody on average, what do you think the average house is worth on a street? They'll say, well, I'll take all the sum of the actual prices over here and then divide them by the total houses, and this would be your average price. And what we're doing here is we're comparing that against actual, and then we're saying this will be, square the number, and this is what we're saying is the error rate of the average. Yes, if you were to do the guess, then this is, what the error rate will be. And what you do is you compare it against the model error rate. So you can see the model is better at predicting. So if a house is worth 200, rather than just using the, average price of a house, so on the street, so rather than just using 300, what you're doing is you are actually using the model prediction, which is actually saying this house is worth 207, and the next one is 242 versus 250 actual. So this is the actual, this is the predicted. So again, you're squaring the numbers over here, and then you get this output. But these numbers, when you get 394 or 25,000 over here, these are not dollar amounts. What you have to do is these are only for the R2 calculation ratio. They are not to be meant to say, you're off by, for example, $49,000 over here, because that's not the case. You're actually off by, $7,000 over there. So instead, what you can use is you can use from the sklearn metrics, you can import the mean absolute error and mean squared error functions. And what these will do is you get this mean absolute error and mean squared error. And the figures are pretty close over here. So mean absolute error is basically on your model's prediction are off by this this $1,000 from the actual price. So in this example, you can see we've got mean absolute error of 8.44. So what we're saying is we are off by $8,000 or so. Root squared error. This is the typical size of the error, also in $1,000, but bigger mistakes count extra. So it's slightly bigger than, and again, this is in thousands of dollars. Whereas, the calculation for R2, that's not in dollars. These are purely a ratio, to generate this R2 metric over here. Over here is where you can actually say, actually, my model is off by $8,000 on average. So you can use MAE, mean absolute error, for root squared error to actually, if somebody says to you, give me your modeled error rate in the actual, the data that you're working with. This is, so in our case, it's in dollars. So we can say it's off by $8,000 or so, rather than if you don't want to work with ratio, though you find understanding ratio is hard. So as part of machine learning, let's try and understand Python a bit more. So we'll start off with this import statement, which a lot of people get confused about. So let's break it down and explain it to you in under 3 minutes. So this import statement over here, you can see there are two styles of import statement. One, which is like this, which is we are importing in the NumPy module. So this is code that somebody else has written, and we're importing it and then aliasing it as NP. So for example, John, you may have a person called John, and John may be called by his friend as Johnny. So in that case, when you say Johnny, that's your short name. You're using, or you might just call him Jay, whatever it is that you want to do, you call him by your preferred name. So you can import like NumPy over here, for example, and you can see that when you do that, then that still works, but then you have to refer to everything like this. So you have to go numpy.array and so on. So rather than do that, a lot of people tend to use NP for NumPy. So that's like your friendly name, like Johnny, and then you can use this syntax over here. But the top line looks a bit confusing. So let's move this down and have a look at this top line. So you can see it doesn't start off with the word import, it starts off with from. The reason it starts off with from is we are trying to import rather than the whole module. So this is the main module, and then within that there's submodule. So rather than import everything in, first of all, we're doing sklearn.metric. So that's the first submodule. So you can see if I do a dot over here, you can see various other modules. There is like impute, inspection, but there's one called metrics. So that's the one we wanted. And then now you see the from part, and now you see the import statement. So this is now this part over here. And then what you say is you actually just want the two functions. So these two functions exist within this module. So we're just importing these two functions and nothing else. So nothing else is usable of this module unless you import it. Now there are various ways. So you can see we imported this in over here. We imported it here and we're using it over here. But you can, if you want, you can just leave this, change the statement rather than from, you can actually do this. So you can have the statement like this as well. So if you comment the top line out, and you can see now though, we're getting an error to say absolute is not defined. But when we run the code, so if I were to run this cell, you can see it still works because Python is able to figure it out. But VS Code is struggling to recognize it. So it goes, I'm not sure what do you mean? So what you have to do is you have to add in the full name like this and then do a dot, and you can see your studio code is no longer complaining. So that's what we mean by this. Rather than importing in the whole function, if you shorten a statement like this into this style, then you have to specify the full name of the module where the function is coming from. So if I wouldn't do this over here, you can see it's complaining at the minute because it can't find that function. But if you comment this line out and leave this one in, and you can see this is valid. So use this style statement is the preferred and the best practice, although you can use this if you wish. But just know that you're just importing in these two functions, and that's all that this is doing. So I hope this explains the complex import statement as part of the machine learning in Python. So previously we talked about the import statement over here and explained how this works. So remember there are two flavors of the import statement, one which looks like this and one which looks like this and one which looks like this. So what's the difference between this statement over here and this statement over here? Of course is this aliasing part. So here we are aliasing it, while here we are not aliasing it. And you can see there's then another flavor, which is you use the from keyword. So rather than the import keyword being the first one, and then you specify which library or the module that you're trying to import. So this is the main module and this is the sub module. And then from there, you can see the import word. So out of this module over here, so sklearn is the main module and sub module, we are trying to import just the two functions. So the yellow color here signifies a function. So when you do this over here and import it, you have to use the names as they are. So mean squared error, means absolute error. So as the names appear here, you have to use them as they are. But what you can do is you can actually alias them. So you can say as mean absolute error. And when you do this, notice now this as have now got a shorthand name. So this is like a friend called, rather than John, or Jonathan, you can call him Johnny, for example. And then you can see over here that we now got an error. This error, if we hover over it, says it's not defined. If we try and run this code over here, although it still works, but what you notice is the VS Code, because the VS Code IDE is complaining. It's saying that it cannot find this function. So what you can do is, rather than refer to it by its full name, you can refer to it as your friend May or Johnny. So here you can do MAE, and notice that this works. So this is a shorthand for aliasing your import statement. Just as we alias numpy as NP, you can actually do it with pretty much anything. So here we imported this function from this library, and what we decided to do was to alias it. And you can do the same with the other one. So over here, you can alias this as MSE, and what you then get is, again, you can see Visual Studio Code complaining that this function no longer exists. If I remove the alias, you can see the error goes away. By aliasing it as MSE, then what you can do is just, rather than mean squared error, you can just type MSE and your code works over here. And same with this one, you can just call it MAE. So just wanted to explain what you can do with the import statement. This is sort of a beginner's guide to machine learning. Check out my previous explanation where I go through this full example for machine learning, which will be really useful. So you can see here we are doing different things. So here's another import statement. Again, notice here, this is the main module, sklearn, and this time we're using the submodule linear module, and then within there we are importing in another module called linear regression.